Before we go fully into talking more on TinyML, there are two things we need to take a refresher on. The first one is machine learning, and the second one is embedded systems or electronics. In this tutorial, I'm going to be giving a refresher on machine learning concepts that relates to TinyML. And don't worry, we're not going to be talking about the big mathematics or big calculations or the heavy theories around machine learning. We'll just be looking at the basic concepts. Machine learning is the ingredient to make our tiny devices capable of making intelligent decisions. These software algorithms heavily rely on data. The data has to be correct and in the right proportion for them to learn patterns or actions based on experience. As we usually say that any machine learning model is as good as the data. Therefore, while building your model, you have to make sure that you are selecting the correct data and it has to be in the right proportion. As an overview of machine learning, we are going to be talking more on the following concepts in this tutorial: linear regression, decision trees, deep learning, neural network, convolutional neural network, and deep neural network. We now go ahead and talk about each of these terms one after the other. And the first one we are going to be talking about is linear regression. We can define this as a basic statistical method used to model the relationship between a dependent variable and one or more independent variable. It's like having some kind of mathematical equation whereby we have y equal to x plus 2, x plus 23. So we have y equal to x plus 23. So whatever we have x is going to be the one that determines the value of y. So given we have some graph, we have the y-axis and the x-axis, and we have some values that are plotted, which is the values of x plotted against y, and we can draw a line of best fit, which can be like this. So the basic rule in linear regression is to find the value of y or the value of x when the value of y is a particular number. For example, if you have to find a value of x at this point, we simply take our point and trace it to the line of best fit and trace it back to the y-axis, and then we can determine the value of y from there. So that's the basic principle behind linear regression. And in the context of TinyML, linear regression can be used for simple tasks such as predicting a single continuous output based on one or more input features. In the context of TinyML and linear regression, we can say that linear regression is an excellent choice for TinyML due to its low computational complexity and also memory footprint. Linear regression is quite easy to implement and interpret, so making it a great starting point for any TinyML workloads. There are a lot of things that we can use linear regression for on TinyML. An example is using linear regression in TinyML could be if you have to predict temperature based on sensor data collected from a small IoT device. So the device collects data such as humidity and pressure and temperature and uses linear regression to predict the temperature. So in this case, we can say that linear regression finds a great application in TinyML. Don't forget we have two data as inputs here, humidity and pressure, and we have to predict the temperature. So linear regression is a perfect fit in this case due to its low computational complexity, its low memory usage, and also quite easy to implement compared to some other forms of algorithm. The second important algorithm that's very common in TinyML is decision trees, and they are basically tree-like structures that make predictions by asking a series of yes and no and questions about the input data. So each decision leads to a branch until a final prediction is reached. Just like we have here, there might be a question that is being asked. So the question is, let's say we have an entering point at this first node. So you ask the question, and whether the answer is yes or no, then proceeds to the next branch. You ask the question until the final branch has been reached or the final decision has been reached. So that's how the decision tree works. And with just the explanation, you can see that it's quite much easier for us to implement something like this on a tiny microcontroller. Now, in terms of decision trees and how they find relevance in TinyML, one thing we can say that it's well suited for TinyML as they offer interpretable results and can be implemented efficiently on microcontrollers. As I mentioned before, it's the simple yes or no questions. It's very easy for us to implement this on a TinyML or a tiny microcontroller. However, we have the problem of overfitting that can usually occur when it comes to decision trees. So the size of the data and model complexity needs balancing. So we can use a lot of methods for us to do the balancing. We're going to be saying this in the coming tutorials on how you can deal with decision trees on TinyML. An example is if you have to clarify a lot of things. Don't forget we have the basic principle of asking yes or no questions. if you have to build a TinyML device that's going to predict whether an individual is walking, is running, or is standing, we can simply take an accelerometer data. It's going to take our value in x direction, y direction, and z direction. And it's going to ask some basic question saying, is the direction in x less than 50, direction in y greater than 30, direction in z less than 20? So based on whether the answers are yes or no, we pass this through some forms of algorithm, some form of processing, and then we can have an answer whether it is running, walking, or standing. So that's concerning decision tree. So very quickly we move into neural networks. And this is very common, one of the most important principles in TinyML. It's inspired by the brain. It consists of interconnected layers of neurons that learn by adjusting connections. So a very simple architecture is having one input layer, one single hidden layer, and then one output layer. For example, we see here, as I mentioned, we're not going to be going into the intricacies or the details of this algorithm much. You can learn more about this in any of the tutorials. So we have 4 inputs neural network A and 1 output. So we pass in these 4 inputs and pass it through a series of hidden layer, lot of interconnected decisions, and then we're able to get the output layer. In a very simple case, we can have a neural network that consists of just 1 input layer, 1 hidden layer, and then 1 output layer. So this is a valid neural network, and based on how complex your data points are, you might determine the types of neural network that you are going to be running for your TinyML. So considering TinyML and its application when it comes to neural network, first we have to say that it's not suitable for typical TinyML due to it's complex to build. A very large neural network takes a lot of memory. It's computational demanding because of the high memory and a lot of neurons that might involve in some cases. And what we can use to mitigate this is having some hardware coprocessors that will be attached to the TinyML device or the microcontroller to make it speed faster. An example is the Google Tensor board or a Google Coral board, so it can be attached to a computer for you to be able to process more neural network easily, not using its own particular hardware now, but using the hardware attached to it as a coprocessor. An example of this, just like I have on the screen, is using neural network as image classification on a low power device. We can use a feed-forward neural network with a few hidden layers. We can train this to classify images captured on a tiny camera attached to the device. And we can see here we are using neural network on a TinyML to predict the image or to classify the image that we have in a particular frame. So more quickly, the next one is convolutional neural network. This is an example of neural network, and the type of neural network particularly suited for processing grid-like data, such as images. We all know that images, they are just typical numbers. They're like matrices of numbers. If you have an image, we're going to have something of this nature. And each of these blocks, there are some form of numbers attached to this. So we can run a lot of processing on this number for our prediction or for any algorithm or any process that we want to do. And in this kind of case, convolutional neural networks find great application. So they use convolutional layers to automatically and adaptively learn spatial hierarchies of features. Just like an example that we have here, there's a lot of things running on in between these layers, and due to its complexity also, it might sometimes be challenging for us to implement this on a TinyML device, but it's still possible. We're going to be looking at a method that we can use to make this much more easier for us to implement it on a TinyML board later on. For TinyML considerations and convolutional neural network, just like in the case of neural network, it's quite challenging for standard microcontrollers due to their computational complexity. But however, there are recent advancements in hardware, and especially hardware accelerations, and there are highly optimized convolutional neural networks now that are open for TinyML applications, particularly those with image processing and capabilities. So an example of this, as I mentioned earlier, is basic image classification on a security camera. So we can use this to identify people or objects entering an area. We can see a lot of applications in this and a lot of use cases for this. So next is deep neural network, and it is quite common. We can simply define this as neural network with multiple layers between the input and the output layers. So they are capable of learning hierarchical representations of data, making them powerful for tasks involving complex pattern. This is quite one of the complex type of neural network, deep neural network. As you can see, the cases I've been looking for before, we have the first input layer, init layer, and then the output layer. But in this case, we have multiple hidden layers between the input layer and the output layer. And with this, we're able to make complex decisions, though it's require much more computational power, but then we're able to make complex decisions and make a lot of predictions using deep neural network. For its considerations against TinyML, generally, it's typically not suitable TinyML due to the large size and computational demands. However, as in the case of convolutional neural network, there are specialized coprocessors that can enable DNNs, which are deep neural networks on TinyML devices. So an example of running deep neural network on a TinyML is classification, such as in wearable devices, and also we can use this for speech recognition. So lastly, we're talking about deep learning. And deep learning refers to a broader field of machine learning that utilizes deep neural network with multiple layers to learn representations of data. So in this case, it encourages various architectures, including a lot of architectures in deep learning. Just like we have looked at before, we have convolutional neural network, we have RNN, also we have DNN. DNN is basically deep neural network that we looked at in the previous slide. So while deep learning provides the foundations for DNN and CNS, there's still traditional deep learning models that are often too large for TinyML. So how to mitigate this is specialized model architecture, hardware acceleration, and efficient training techniques. So if you're able to gather all this, we'll be able to train deep learning. We're able to have deep learning that are able to run on TinyML and resource-constrained devices. A very simple example of deep learning in TinyML is predicting maintenance in industrial machinery. So you can do this by analyzing sensor data coming from a machinery using deep learning techniques. So pattern indicative of potential failures can be detected early, enabling timely maintenance actions to be taken. If you're going to track the noise coming from a particular machinery, we can know if the noise changes, and then we can take predictive actions or preventive actions before the equipment finally runs out. So these are basically the algorithms that we consider in TinyML and machine learning. We looked at convolutional neural network, deep neural network, decision trees, linear regression, and also new deep learning. So now we're going to be looking at some of the issues that we have with this network, with this different algorithm, and how we can make them better work on a tiny microcontroller.
One last thing before we round off this tutorial. It is important to note that in TinyML, where resources are limited, the size of our model plays a critical role. Traditional machine learning models can be quite large, requiring significant storage space and computational power. But in TinyML, we don't have the storage space and computational power available to us. So the question is, how do we solve this problem? We have large models but tiny devices. And this is where quantization comes in, which is basically taking the large models, shrinking them for efficiency.
After knowing the solution to this problem, which is quantization, basically we define this as shrinking the model for efficiency. What are some benefits of quantization? Basically, I'm going to talk about two, which are reduced memory footprint and faster inference. With reduced memory footprint, smaller models require less space on the device. So with this, we are allowing for more complex models to potentially fit on TinyML devices. If we're able to pick our very large model, we're able to shrink it using quantization. With this, we're able to run a very large model on a small microcontroller without any form of issue or the device getting overheated or not being able to carry the model. And the second one is faster inference. Lower precision calculations typically require less processing power, so leading to faster predictions and improved battery life. If you don't have to make a lot of calculations, the precisions for our calculations are typically low, which this is going to require low power. With this, we're able to run a very big model on a tiny microcontroller in the case of TinyML. So that's it for this tutorial. We've looked at TinyML and some relevant algorithms we use in machine learning when it comes to TinyML. In this tutorial, we're going to be looking at just some brush-ups or some revisions on electronics, because we need to review our knowledge of electronics and embedded systems before we start working on different projects using our different TinyML boards. So see you in the next tutorial.